to share screen because I've raised team before.
Yeah, maybe I can just quickly introduce him. So we have Muru giving a talk to us today on his recent work on large-scale data selection for instruction tuning. Muru is a first-year PhD student at USC, advised by Swabha Swayamdipta and Robin Jia. And his research interests are in large language models with a focus on model internal driven understanding and efficiency. He also works part-time at Together AI as well. Take it away.
Yeah, thanks for the introduction. Are you able to see my screen?
Yes.
Okay, cool. Yeah, so I'm just going to present this paper on data selection that we recently do. I don't like particularly work on data selection, but I guess through this paper, I also get like a somewhat in-depth exposure of the field, and especially because AR assigned me 6 papers on data selection, that's also like forced me to get a more in-depth understanding of this field. So as you would say, this was a project that started when I was at UW, where I did my bachelor and master. So this was a collaboration with some UW people and some AI2 folks. So I would particularly say that the first author, Hamish here, he's like a very expert in this data selection stuff. So if you have any further questions regarding the material, I think he's also a good person to reach out. I think data selection in general, I feel like it's a very empirical field, or actually like anything involved data is like very empirical. So I think the paradigm is consistently shifting. So it's always the people who has like the first person hands-on experience that can give you the most insights of this. I think I learned a lot throughout this project. And I think someone like Hamish who keeps training this kind of models to also have like great insight on this. But yeah, I think for now, I'm just going to mainly focus on our papers because yeah, I think it's also so I think I would love to just like keep this interactive. So if you have any question, feel free to interrupt me, or if even you just have any like discussion point that you want to raise, feel free to interrupt me, and we can talk about it as well. Okay. With that being said, so this is not a paper that say like propose a new method that beats X baseline on Y task by a Z margin. It's more about a re-examination of the existing data section methods for instruction tuning. So I think the insight of this paper that wants to offer is that at this particular setup that we study, we believe is like realistic for instruction tuning. Like what conclusion could you draw for the data section methods we studied? So I would try to make it clear of what we study and what we don't study, because like data section is such a gigantic field with like so many prior orgs, and no one can really aim to give like a fully comprehensive review. So, but at least I can make it clear so you can draw the judgment yourself. Okay, with that being said, so as I mentioned, there's just like so many data section papers. There's just like so many. I think no matter how much baseline you put in your paper, there's always going to be reviewers saying you missed like one of the baselines. So I would just say like these are the methods that we study in our paper. I think there are 9 total. So you can broadly categorize the methods into 2 categories. One is validation sample based. So it requires you to have a validation set X that requires the task or the capabilities that you want to train your model on and use that to select data. So it could be based on the representation. So you can use a embedding model to get the embedding similarity between your validation set and the data in your candidate pool, and maybe draw out the data that has like higher similarities. You can also use more model-based representation similarity, where for any model you want to train, you collect the representation from that model itself. This approach, we call it RDS. So I think the only difference is whether or not you're using external model or you are using the model you want to train itself to collect the representation. Because I think this notion of model-based, I think it's like intuitively might be helpful because the model you want to train might give you the best judgments of, you probably want to draw the judgment from the model you want to train itself. So there's also a slightly more complicated approach that is, I think people call it influence function. We studied last, which is also a relatively recent paper that studies this. which is basically just using the first order gradient information to draw this to feed into this formulation of influence function. I think basically you can, so there are beautiful maths for influence function. I encourage you to check it out. But at the very end, I think you can also just think this as this uses the gradient information to compute the similarity, because there are lots of approximation going on. Like this is like a first order gradient approximation. Some prior work use like second order information, but all of them are approximation. I think you can also just remember this by like what information it uses to do this action. So there are also validation sample free data selection methods. I think these are more like, because we don't have a validation set right now. Now you want to select the data just by some inherent property of the data itself. So it could be by perplexity. So prior org have tried to use like, given a pool of data, we pick out the data that has like highest perplexity, because that might be the data that the model is worst at. So notice that this is also going to be model based. There are also like cases where people just take out the data with like median perplexity range, because they might imagine the highest perplexity one might be just like data itself is bad. So there's this like in IFD, I forgot the full name. This is like measuring the difficulty of the data itself. You can also just imagine to score by like another language model. So I think, sorry.
Sorry, quick question. What is the IFD doing?
So IFD is trying to measure how difficult your given sample is. So the naive way is just to measure by like, because we're doing instruction tuning, so you just measure by the loss of the answer given the instruction. But it could be inherently the data is like easy or hard. So we additionally normalize by the difficulty of the answer itself. So this is again still trying to figure out like what data is still difficult, challenging for the model itself. And I think this is like intuitive
we
notion,
have
but
so A here is the sequence, the instruction tuning sequence, is it? Or is it?
So Q and A is just the instruction and the response.
Oh, I see.
Yeah.
And both is scored with the same model.
Yeah, so usually you would want to use the model you want to train yourself to do this, because again, I think the notion is that you want to figure out what data is more challenging for this model that the model still need to learn more. Yeah, I think this is like another way you can categorize this data section methods. I think a lot of them are model based because they're trying to figure out like what data this model should learn. So it probably doesn't make much sense if you use another model to like estimate the difficulty, because different model might be good at different stuff. Yeah, I'm just trying to give like a brief intuition of all of these methods. There's like some details that you can find out in their corresponding paper, but I'm just not going to go too deep here. There are also another approach that from a quite different perspective. It's just like that people call data model. So this is basically predict how the model perform a given training set. I think this is not like very scalable yet. Again, it's a interesting perspective, has some like beautiful notions, but we didn't study that in this paper because it's just like we haven't found it could be realistic scale up to a large sample yet. What it does is that you train a model to predict given training sets, how your model after trained can perform on the test sets, which I encourage you to check it out as well. So okay, so these are the methods that we studied, and I think another important thing to cover is that what is the setup that we do. I think instead of saying that this paper is more about methodology novelty, I think it's more about like setup novelty. So we really examining all of these data selection methods unified in a realistic setup, because like, each of this prior paper would claim that they're state of the art, but you just cannot be like everyone's state of the art, right? So I think in a realistic setup, we are trying to see like what conclusion holds and what conclusion does not, and what property of your data section setup matters. So again, I think generally this action is just like given a large pool of candidate sample, you want to select the best subset for it. And in this paper, we particularly care about the instruction tuning setup. So I think the common setup in the existing paper is that they're using, like, for example, Alpaca or FLAM-V2 as a data pool. These are like relatively old instruction tuning data sets. The selection size is usually less than or equal to 10K, and the evaluation is often less than or equal to 3 tasks. So in our setup, we use this Tulu2, which is the open source instruction tuning datasets released by AI2. They use this to train the Tulu model. So I think the publicly released version is a 1 million sample filtered datasets, and we use the unfiltered dataset, which had like 5.8 million samples. So compared with something like Alpaca, which only have 550K examples, I think this is like a significantly different range to study. And it's also the case that 222, I think in general, is of higher qualities than Alpaca and FLAM-V2. So I think this is also like a subtle notion that you can think about if you're mainly selecting data from a higher quality data pool or a low quality data pool, because sometimes the method might work better as a filtering tool. So in that case, trying to select, there might be a method that makes more sense to use for selection in a low quality data pool, because maybe the usage is more about like filter out the low quality data samples. And for the selection size, we also we did a bunch of experiments. We vary from like 10K to 1 million. I think it's so like I'm not saying like less than 10K doesn't make sense. Sometimes people care about efficiency, so you select for a small size and try to get like the full performance. But I would also say that probably people today don't care about 10K versus 100K. Maybe you care a little bit about like 5 million. So I think it's still reasonable to think about how you can select a subset given this range. But I think for to be realistic, we want to do relatively large section that is more aligning with the modern instruction setup. So evaluation also matters. I think prior org usually they often have like less than to 3 tasks. It's also not very diverse. Some paper only evaluate on like Alpaca Evo, for example. So in our case, we evaluate on 7 downstream tasks that has like multiple choice question, the knowledge intensive ones like MMLU, the short question answering, math code, and chat dataset like Alpaca Evo. We also consider doing multi-task selection. So in previous slides, there are like some data selection methods that based on validation samples. So it could be, so for single task selection, it would be the case that I give the validation set for one task and I want to select one subset of the data that tries to outperform good on this task. But usually the case is that you probably don't want to train one model per task. So it's usually more of the case that you just have like a bunch of samples coming from different tasks that generally represent a group of capabilities you want the model to have, and you use that single validation set to select the one concrete subset and train one concrete model. That's what we call multi-task selection in this case. Okay, it's a setup here. I think it's in this paper it's important to like know the setup difference, as it's like a more I guess it's more illustrative difference of how our candidate pool is different from the previous ones. So both in the size, we're much larger, and also our data pool has like much broader distribution of data coming from different sources. I think this is just like a clear illustration of our data pool is like much more diverse and higher quality and large compared with the previous ones.
What's the difference between Tulu 2 and Tulu 3?
I actually don't know. I would imagine, so I'm pretty sure their data set, so their details on this, they release every detail about like the composition of the data sets. I would imagine this is just like better human curation of like what sources you should draw it from. I think Toulouse 3 uses some of the recent data curation work that tries to create some synthetic data, generate some synthetic responses. I think I think a lot of the data in like this kind of data sets are having response generated by some large model like GPT-4. So I guess the difference could also just be like now we have stronger models. Usually the response is like refreshed by a stronger model.
Makes
I think
sense.
there are details about this, and you can check it out in their websites. So we mainly did the results. So I think if I didn't specify it, it would by default we are doing the experiment on two unfiltered data sets, but we also have one result on 2 3 as well, because I think it's like by the end of we wrap up this project, 2 to 3 came out, and so we also did one experiment just as like a out of domain transfer, I would say. I think 2 to 3 is like yeah, it's like released like maybe 1 year or something like after 2 to 2. So it's like a good test bed to see like whether or not our conclusion still holds for different data sets. So okay. So with all of the methods I presented here, I would just say that we find that this RDS plus that works the best, which is simply that. So which RDS is simply that you take the representation, you give a data sample, you pass that to the model, and you take the representation and you match the similarity with the validation set you care about. Because everyone's working with a autoregressive decoder only model nowadays, so just like the usual way of getting a representation, which is like you probably pull the last layer hidden states, doesn't make much sense for like a autoregressive decoder model. So what we call RDS plus here is that we did a weighted average of the final layer hidden states. I think it's by emphasizing the hidden state on the early token more, because I think I think it's either emphasizing the early token more, emphasizing the late token more. I think it's probably emphasizing the late token more because like the late token hidden states also have the information from the early token, but the reverse is not true. So during the weights average, you probably want to give more emphasis on the later hidden states. But yeah, I think this like representation, like you just take the mean pooling of your hidden states from the model. It's like something people definitely have tried before, but we find that in our case, it performs the best, outperform every other data section methods. And I think we find that this like RDS plus, where you take the weighted average, can like give you a small boost, like something like 1 or 2 points. But I think overall, the takeaway from this table is that we have the random unbalanced baseline and the random balanced baseline. So balance means that you sample from your candidate pool with a balanced distribution. So according to the full distribution of your candidate pool. So you can see that a lot of the method doesn't even beat the random baseline now given the high quality data pool. So I think this is like a distinction you can draw from prior work, especially if they're working on something like FlamV2 or Alpaca, is that those datasets are relatively lower quality. Sometimes what you can find is that you can select a subset and it can even beat the full fine-tuning on the full datasets. It's because the datasets pool quality is just like low. And in this case, you can see that even just doing a randomly balanced sampling, you can get like a fairly good performance already. I think promisingly RDS can outperform the random baseline on like every evaluation set you have. So it's not like it's particularly biased toward evaluation. It's like it's basically works for like all of the tasks that we consider here. And notice that this is like we're only selecting like 10K data points for a single task from a subsampled pool, where we subsample like 20K data points from the 2 to 2 data sets. So I think overall RDS performed like very great. This last, which is like the influence score first order gradient based method, also performed pretty well. But I think one thing you want to remember is that it's very expensive to compute last. You basically need to compute one forward pass and one backward pass on every data you have. So I think another thing you want to think about is like whether or not it is worth to run your data section method, because the cost of running it might already outweigh the cost that you save from training on a subset of the data. So I think just to further press all these points, I would say a lot of method doesn't even benefit from using a large data pool. So on this slide, we're showing selecting data points from 200K data points candidate pool. So on this slides, we have like 2 points for each of the methods. So we are selecting from 200K samples versus we're selecting from the full 5.8 million samples. And you could see that except for RDS plus, no methods actually benefit from selecting from a larger pool. So I think this is a distinction that maybe shows that these methods are bad at just like drawing informative information from a very large pool. They don't really work too much better compared with if you just have like a relatively small pool. And we also have the multitask scenario where now you basically just have like you have to train one model that is supposed to perform well on all of the 7 tasks here. We can see in this case again, RDS plus performed the best. And we also, so previously we talked about like, so RDS is like validation set based. You have to have, we here in this case, we have like a few samples from each of the tasks we have here and use that to construct our validation set and measure the representation similarities. But one thing you can think about, so one concern you might have is that there might be the case where you don't have such validation stats. So we try to just use like some external information as a validation stats. So we try to use the wildchat and arena hards samples as a validation set here. And I think the arena hard one also performs like fairly well. And as you can expect, the arena hard one performed especially good on alpaca eval. I think this is because, yeah, arena hard is generally this kind of chat style data set. So the style is more similar to alpaca eval. So if you use that as a validation set to select your data, your trained model is more likely to perform well on something like alpaca eval or maybe like JSMK as well. But I would just say this also give you promise that the RDS probably doesn't rely that much on the particular validation set you have. As long as you have like a high quality validation set, it's probably able to select you high quality data as well. I think Arena Hard and Wildchat in general are like this kind of fairly diverse chatty style data sets. I personally think if you have a very narrow domain set here, it's probably unlikely that it's going to perform well across the board. So I think thinking about what domain you have in your value set is an important thing to think about as well. So you can see we additionally have a Tulu results here. So what does this row mean? So this row is the model that you train on the handcrafted, I think three. So all of the number here are selecting 326 K samples from the full Tulu unfiltered pool. So the reason we do that is because the original Tulu model is trained on this number of samples that is hand curated. I mean, so like by hand curated, I mean that the human select what composition of data it should come from and do like some moderate filtering to construct the data set. So this is like the Tulu model that is actually released with the human curated data set composition. And we find that the RDS model can outperform it despite we are using this kind of automatic data selection methods. I think the result here shows that, I think the result we have here that shows that a data selection method that can very reliably outperform the random baseline and also can, beat the human curated data sets by a small margin. It's like pretty promising. I think this is like the conclusion that every prior paper would like draw to say, okay, we definitely perform better than random baseline, sometimes perform better than the full data sets. But I think our result shows that I think this conclusion might just be an artifact of you using a smaller data pool, you're still selecting too few samples. I think it's still an impressive result that you do have a data selection method that outperform both the random baseline and also the human curation. And I think that's the main message I want to deliver for like these tables. So we also have this like additional plots, which shows that RDS plus really beats random baseline across the number of samples you want to select. So from 10K to I think 4.5 is just like you're using all of them, so they have the same performance. But across the board, from 10K to like 2.5 millions, the RDS is always beating the balanced random baseline. I think another thing you can think about is, okay, so to do RDS, you have to run one forward pass for all of the data you have. And how does that transfer to the total flops cost? So if you compare the flop cost, you will see that because as long as you do RDS, you need to run one forward pass on 5.8 million samples. And so the cost of the method is the cost that you use to select the data plus the cost of you use to train on the data. So I think training on one data samples can be relatively estimated as 3 times the forward pass. So as you can see, because of that, starting as long as you start to do RDS, it has like very high flop cost already. So I think this is like you're selecting only like 0.2% of the data sets. It's more costly than just randomly selecting like 43% of the data sets with the random baseline. So, but you can see that after you increase the selection size, RDS like pretty quickly emerged to outperform the random baseline. So when you are selecting 5.6% of the samples from your candidate pool, it outperforms using like 43% of the data with a random baseline. And in this case, I think the flop costs of them are like relatively the same because the training costs of using this like much larger selection from the random baseline is outweighing the selection cost from the RDS. So I think this plot is saying that even you take the flops into account, which a lot of prior method doesn't do. RDS still can offer you a greater frontier margin that you can consider using that. And I guess using a smaller subset in general might be beneficial because probably it's easier to distribute. It's probably easier to reproduce, to do like iterative experiment, extra. I guess it's like probably relatively minor, but I think this plot is like shows that RDS is like really promisingly reliably outperforming the random baseline, and it could be a method that you should consider in your realistic setup. I think like this kind of message is actually, I think, pretty hard to deliver unless you have like a lot of this kind of experiments. So as I mentioned before, after Toulouse-3's release, we also attempt our method on Toulouse-3 to see like, yeah, we did all of our experiments on Toulouse-2. So it's definitely good to just try that on a different data pool. And so we find that like pretty promisingly here, RDS plus still like outperformed the Toulouse-3 SFT, which is like, I think, yeah, human-curated one. I forgot the exact number, but we're trained on the same number of data, and we find that, yeah, the Toulouse-3 SFT also, we can also outperform Toulouse-3 SFT, which is using the human-curated data composition. And I guess somewhat surprisingly, the arena hard performed like pretty bad here. I think this is like similar to the prior observation where arena hard is particularly biased toward alpaca eval. So I think in this case, I think it seems like it's too biased and resulting in a much lower performance on things like TidyQ and Big Bench hard. So which resulting a low average score overall. Okay, I think that's it. I think there are a few additional tables in the paper. Feel free to check it out. But in general, this is like a paper with a lot of experiments, and we're trying to just like give an overview of the data section methods. I think TLDR is that the setup matters a lot. So the size of the selection, the quality of your pool, those can affect like which dissection method works. And sometimes if you're in a particular setup, some dissection methods might not even outperform the random baseline. And the complexity of the selection method itself should also be taken into account. So there's also this great paper, compute constraint dissection from Sasha's group, that basically tries to do sort of a scaling law for doing data selection and figure out whether or not it really makes sense to use the data section methods if you take the flops into account. And so compared with their paper, so we have like a higher quality data pool and like a relatively more realistic evaluation setup. And I think we also have more data section methods reviewed in our paper compared with theirs, but I think they are doing more experiments just like on this flops plots with all of the methods. So it's also offer like slightly different insights compared with ours. So I would encourage you to check it out as well. And yeah, I think overall the table just telling you that, yeah, this RDS plus works the best and does offer you the computational advantage. And yeah, I think this is not a small thing. This is actually a pretty hard thing to conclude. And yeah, I think that's it. Feel free if you have any questions.
Thanks for the presentation, Muru. Are there any questions?
Hi, Muru. I had one quick question that I wanted to ask you. When you were, great paper, by the way. When you were taking the weighted average of the hidden states, how did you learn the weights that you were the weights for that? Was that handcrafted?
Yeah, it's handcrafted. We didn't learn it. It's basically just it's a handcrafted way that assign higher weight to the later hidden state.
I see. How did you like decide to like handcraft? Or was it just like you gave more weight to later tokens?
Yeah, I think the general intuition is to give more weight to later tokens. So I forgot what's the exact weight that we're using, but I guess you can imagine that to be some like just like some sequence of weights that's generally decrease as you go to earlier tokens.
Okay.
I'm curious to hear about how do you think things would change if you use a noisier data set, if you have a noisier pool?
So we didn't put that in the paper, but I think previously we also use this alpaca eval as we also use alpaca as the candidate pool, and I think on there something like last actually performed like pretty well. So I think last which uses like the gradient information that is supposed to be more expensive. I think it might be better at like filtering out noise. So if you are particularly concerning about, I think that's the important point is that if you have a relatively noisy candidate pool, then in this case, maybe you just don't care about the cost at all because you cannot train because if you assume that training on the entire pool leads to a bad performance, then you're probably willing to take whatever cost to filter out those noisy data sets. And I think something like LAS, which is expensive by itself, but could probably be more useful for filtering out the noise examples. And I think, yeah, on Alpaca, we find that LAS performed pretty well. So I think that's a good signal for it.
Any questions from anyone else? Otherwise, I think I have.
Hi, yeah, I have some questions. Thanks, Muru, for the great talk. So what's the requirement on the validation set, right? I think you're using that to select, basically to measure some way of comparison. If does that need to be somewhat representative to the task you're trying to solve?
Yeah, so actually, so like for all of the number here, we're actually directly using the validation set of the task as a validation sample. So that's like highly correlated with the downstream task that we care about here. So yeah, so I think that's why we did this additional 2 experiments because sometimes you might not know like what concrete downstream task that you care about. So we try to see like using a external high quality data sets as a validation set. Does that work? Yeah, I think that worked to some extent. We don't have like I think because on Tunus 3 the result is so mixed, so I wouldn't draw like a very conclusive conclusion here. But yeah, I think for all of the rows here, we're using validation set that is like highly correlated with the
Yeah. So the assumption is that the validation data set already is high quality, right?
Yeah.
Okay. And the other question.
Yeah, I think the quality and the domain both matters.
Okay. Yeah. You have to start somewhere, right? So otherwise it's tricky. The other question I had was like how do you see this generalizing to imaging tasks? Is there anything that would need to change? I guess you would need different types of models to get embeddings.
So I think for a method like RDS, this is relying on you're collecting the representation from the model you want to train. I think this model-based notion, I personally think is like pretty intuitive and makes sense to me. So I feel like the first thing you could try is always to just like collect the representation by the model itself because that's probably the most like you want to train the sample like no matter you're measuring difficulty similarity, you want that to be like based on the model you want to train itself because this notion could be different across different models. I think in general for text to image transfer, like I don't see a particular point that would be different there. But I guess because that's a totally different field, you're probably going to have different conclusion as well. I would imagine maybe for the image domain, you have more noisy samples. And I think, yeah, in that case, I would also imagine so I guess that depends on the concrete data set you're using, but especially for those like text captioning data sets, which I think are like the widely used for pre-training some of the image representation models. Those are probably first have like high noise, and second, I think there are some inherent property that you can utilize there by like measuring the alignments of your caption with the image, something like that. So there are probably like also other this kind of data section method that you can think about in that scenario. But yeah, I never work on or read the data section paper on image learning. So generally, I feel like if you transfer to this like completely different setup, there's going to be something that is going to be changed.
But I guess the algorithms themselves are, I mean, you can run all of these selection algorithms on any model, right? Like, it doesn't even need to be sequential data.
Yeah.
Like, it doesn't need to be this autoregressive kind of sequences either.
Yeah, I think the overall methods can transfer to any field, and especially like this kind of influence function. I think it's I think it's actually used in computer vision a while ago when like computer vision is the most popular AI task. So I think a lot of them can definitely like all of this notion, like the overall methodology perspective, can definitely be transferred to a different domain and modality. I think it's just like you might need to alter the detail a little bit. For example, if you're collecting representation from a diffusion model, you probably use a different methodology compared with the weighted average we have here for the autoregressive model.
Makes sense. Do you know what happens if we only use the last tokens embedding or last token activations instead of the weighted one?
I think we have tried that. I think that actually performs similarly to use the weighted version, but weighted version performs a bit better.
Slightly better.
Yeah. I think the weighted version is like slightly better than both using the last hidden states and also using the unweighted average. Yeah. But I think the margin is like small on the validation that we have, and yeah, I think maybe all of them can work.
Does anyone else have any questions on this?
I'm also interested in kind of visualizing the data. Have you done any work in this direction? Like, I'm thinking these kind of dimension reduction techniques like t-SNE and UMAP. Have you tried to visualize like how close data samples are compared to your validation set?
Yeah, that would be interesting. We didn't do that. I think we so I think previously we have some like this kind of visualization just like to visualize the distribution of the representation similarity, something like that. And especially because we need to do this kind of multi-task collections, you want to think about how to aggregate the similarity across different validation samples. I think yeah, that's actually like one small detail I didn't cover is that the RDS, you have the validation, you have the representation for each of your validation set, and you have the representation for each of data points. And how do you aggregate the similarity? I think what we do is like we do sort of we don't actually just like take the average of the similarity. We actually do this kind of round robin selection where you take the sample that has like highest similarity to like one particular sample from one particular set and like take one for each set individually, something like that. I think that's because we find that sometimes there could be tasks that like the task itself could also cluster together. So if you're taking the average, it would be like significantly biased toward a set of tasks here. I think it's because alpaca eval and probably codex, the representation of these two tasks are like individual clusters themselves, and the rest of the 5 tasks are more or less clustered together. So in the multi-task setup, if you just take the average, it's going to be significantly biased towards the 5 tasks you have. But if you're using a round robin selection, it actually all performs good on like every tasks. So yeah, we didn't do like something like t-SNE on all of the samples. I think that would be interesting. I think one thing that we could do more in this paper is just to do more analysis on like what data selection method selects, and yeah, in general have this kind of representation visualization to give a broad sense of how data are similar to each other. But yeah, there are, I think, a few exploration we did to figure out what's the best way to aggregate the multitask information.
Yeah, I see
Yeah,
you have some
that's-
histogram, right? In your paper.
Yeah,
kind of- yeah.
I have that. Let me see. I think probably in the appendix. Are you talking about which one? Which figure are you talking about? Like
Figure 5, right?
Yeah. Okay. Yeah. So yeah, figure 5. Yeah, figure 5 is to I think figure 5 is visualizing the RDS score, which is like the cosine similarity between the validation set examples and your data pool examples. I think this is like showing you that how you will generally have a lower average similarity than GSMAK. So if you, for example, I think another thing we consider to do multi-task selection is that you just select the highest cosine similarity, no matter what validation set that is corresponding to. But that also doesn't perform well, and that's why we have this visualization, is because there are some data sets that just inherently going to have lower similarity with all of the data samples. And so in that case, you also probably don't want to just consider the absolute number. I think figure 6 and 7 is probably, interesting to look at. I think these are visualizing the data composition that is selected if you use a particular set as a validation set. I think this is like showing you that different set definitely select like very different compositions, and also different data selection methods also select like very different compositions. I think, yeah, if you look deeper into it, there's like some qualitative, I think there's some qualitative you can draw. I think for something like, for example, Codex is like a code data sets. And I think, yeah, it does select a fair amount of code alpaca. I think this is because like there are some data sets that just generally have like lower composition in the overall sample. So even though you're already selecting a lot of them, they might still only constitute of a small portion of the overall sample of your 300K samples. Yeah, I think if you look deeper into this plot, you can actually find out that I think the composition selected by each data set actually like makes sense qualitatively to some extent.
So
Yeah,
if you select data based on similarity to a validation set, isn't there a risk that you're throwing away kind of valuable examples?
In the sense that you cannot train on this validation set.
Let's say like you're trying to train from a new data set, right? Like maybe you're doing some sort of fine tuning. But if your new data set includes some sort of valuable samples that are living on the tail of the distribution, you would be throwing them away, right? Because they might not be close to your validation set.
Yeah,
Let's say I'm thinking of, like autonomous driving where you have freak accidents happening, right? They're probably not close to whatever the original validation data was, even if that data is very high quality. But you actually care about the models improving on those kind of rare occasions. Like in healthcare, we have a very similar issue that there are a lot of rare diseases, right, where we only have very few data points. And especially if you think about a federated learning scenario, right, where we want to have multiple hospitals joined together, they all might have different distributions, but those are ultimately helping your model to be more generalizable and working better on the rare cases. So now I wonder if a data selection is actually somewhat harmful in this scenario.
Yeah, I think that's a very good point. I think it's not even just about validation stat itself. It's about generally this line of method is trying to find things that is more similar to like some held out stats. And I think,
Right.
yeah, I think with this notion, it's going to discard some of the out of distribution, some of the tail scenarios. And that could be very damaging for the cases where you do care about those. I think the text data sets we have here, the instruction tuning setup is like generally, I would say like they're more or less coming from a broad but like still within control distribution, and it's like model has been preaching on so many data sets, so it's not the case that you really want the model to like there like some fairy tale stuff that you want the model to know. So I think the similarity based approach worked very well on the text domain, but I agree that on domain that you mentioned, it might not be the best way. I think some of the methods that uses like use some of the inherent property of the data itself. Like for example, I think like the IFD I mentioned, which trying to estimate the difficulty of the data itself could be useful in that case. Like I think this is just like overall a very different perspective, a very different notion. If you're using the similarity as the main to select your data, I think you can also imagine so like yeah, like the no, actually, yeah. So yeah, I think using the similarity to select the data is going to definitely give you a different result than
Yeah.
using the difficulty to select data. And also something like the last, which uses a gradient information. I think I think the mathematical intuition of that is that you're directly estimating how much impact do you have by training on this particular sample, on your validation sample. So that's not based on the difficulty nor the similarity, but it's like a more direct way to estimate the impact. I think that could also be useful when you have more out of distribution or like complicated data relationship, even though it's expensive to run.
Mm.
Yeah, I guess this is a pretty philosophical question, or like a pretty interesting technical question, right? Like what distinguishes outlier from a rare example?
Yeah. I think like for example in the IFD, in their notation, so yeah, I'm still sharing. Whatever. Yeah. So like yeah, in those difficulty-based selection methods, they also have to define threshold. Like beyond the threshold, we consider this as like a bad samples. So it's like usually that you have to figure out that's like a very subtle line that you have to decide for something because yeah, I think I agree with both sides. It's hard to distinguish between those. So some I think human judgment might also need to come in here, especially when you have like this kind of very complicated data scenario.
I kind of had a question building off of Dr. Roth's question. Um, like, I guess, like, in some sense, when it comes to like choosing these validation sets, at least in this example, like the query sets are like, I guess, quite small based on the size because the algorithm is like non-parametric in respect to these query sets because you're iterating through all the elements in the query set. And I guess in some sense, like, do you think like the limited size of these query sets might also like kind of not be able to like encapsulate the entire distribution of rich data? And like, would that be something limiting about like the technique of like, scaling this query set might be computationally heavy? If you want to try and include like a bunch of like I guess niche like rare diseases in this case.
Yeah, I think that's a very good point. So for a single task selection, we can do something like as few as 8 examples for GSMAK and get good performance. But that's because GSMAK itself is just like a very in distribution evaluation case. So if you want to train a general purpose, broad, let's say a language model, I agree that it's probably just hard to construct a small validation set that can encompass the distribution that you wanted to have. So I think that's why we consider to use something like Arena Hard or WorldChat as the external validation sets because those are large size, relatively higher quality. So this is becoming more like, given a high quality instruction tuning data set, how do I select more high quality instruction tuning data samples? And in that case, it can probably elevate the distribution issue a little bit because you start from like a well-distributed data section, well-distributed data sets at the beginning, at the first points. And I think, for example, for the medical domain that you mentioned, I think it could also maybe be the case that you start with like a continued pre-training data sets of you maybe subsample it, but keep the distribution and use that as a validation set to select like further examples. So I think one way you can maybe elevate this is by doing this iteratively. We didn't try that in this paper, but could be something to consider if you need to scale up the validation set.
Maybe one last question. I think we're reaching the end of the time slot.
I guess another question I had was, like you guys opted to use cosine similarity for the the embeddings from like your data set to your query set. I guess like was that like choice motivated by like computational efficiency? Like why not train like a small lightweight classifier on top of these image embed or on top of these like embeddings to like give like a I guess not a more robust, but like just like yeah, what was the motivation for cosine similarity?
Hmm. I think that's just because we just want to capture how your model thinks these two samples are similar to each other. So like cosine sum is just like a natural way to do that. If you train additional model on it, it could be, I think there could be two cases where the first the model itself is like too weak. So if you train a model, I think the thing you want to is you have to give a label, right? So I think it's unclear what supervision you should have it here. So you probably need to like handcraft a bunch of labels that like how you classify should classify this two example as like more similar or like less similar to each other. And I think the benefits of using consistent is that it's unsupervised.
Yeah.
Yeah. Oh, yeah. Sorry, I had a question I forgot to ask. Do you, it relates to a lot of the questions which came up, but you seem to try increase the diversity of the selection by doing this round robin. Like that's the aim of that seems to be to make it more diverse and representative, so that you don't just keep selecting the most similar data points again and again. Do the other methods also do this, or is this only in RDS?
So for multi-task selection, we do round robin for all of the tasks, for all of the validation sample.
And also for data points, right? Like you go per data point and select the most similar one, you were saying.
Yeah.
But in things like less or the other examples, I think they just select the most similar stuff and that's it.
So I think in all of the validation sample base, you like in a single task setup, you select the most similar ones for each of the data. So I think in the original last paper, yeah, they probably just like took the average and select the most similar ones. I think we find that perform worse than doing round robin.
I see. So you use round robin for the other methods as well.
Yeah.
Okay, makes sense.
I have a quick request. I just saw the code base on GitHub, right? As far as I see, there's no license file. So
okay.
If you have a chance, could you add one? Then
Sure.
it makes it easier for us to maybe integrate with your code.
Yeah,
in,
totally.
in MONAI.
Thanks for notifying that. I didn't realize that we don't have a license.
Yeah, that would be great. Yeah, thanks. We'll take a look.
Thank you so much. Thanks for all of the great questions.
Thanks, Muru. This was really great.
Yeah, very interesting. Thank you.
All right. Yeah. Looking forward to catch up with you guys in the future.
Thanks. Bye.
Thank you. Bye.
Bye-bye.
Bye.